Hi, my name is Adi Mata, and today I'll be talking about triple integrals for multivariable functions in the Cartesian coordinate plane, cylindrical coordinate plane, and the spherical coordinate plane. So first, let's get started with the triple integral over a rectangular solid box. So for f of x, y, z over some box that's defined by b, where b is Cartesian coordinate plane, and x has these constraints, y has these constraints, and z has these constraints. It's defined as this: the triple integral over region B of f of x, y, z dv, three-dimensional constant of integration, and a triple integral is defined as this. Let me get a new marker. So what this equation actually represents is an approaching infinite number of tiny little volumes defined by some delta x, delta y, and delta z times our function here at those points, which integrates the function over some region B, where B in this case is a rectangular solid box. Now, what if it's not a rectangular solid box and it's something that's a little harder to integrate, but nevertheless we still need to integrate over? We have the triple integral over a general region. So for Cartesian coordinate plane, for general regions, this is how we solve for it. Our triple integral over a region E of f of x, y, z dv is equal to the double integral over the projection of solid E onto the xy plane. D is our projection of the integral from u2 xy and u1 xy, where u2 is basically the top of our solid and u1 is the bottom of our solid. I'll draw it right after this. And dz because these are z values, and dA because D is a region that has area. And E here is defined in the Cartesian coordinate plane with this as its projection, and its top and bottom being u1 and u2. And how that looks on a coordinate plane is this: z, x, y. So we have some solid here, clearly not a box. It goes like that and comes down here. And this entire box is E. And now it has like the projection onto the XY plane, kind of like a shadow, where this little circle down here, well, not really circle, but you get what I mean. This is D. And this top part here is Z equal to U2 XY, which is our upper bound. And this bottom part here is Z equals to U1 XY, which is our lower bound of this non-rectangular solid box. That wraps up general regions for Cartesian coordinate plane. Pretty simple compared to the other ones here, which are a little more abstract to think about because we're not really used to those graphing systems yet, like in this level of math. Now for the cylindrical coordinate plane. So for the cylindrical coordinate system, first off, what is it? As we already know, the XY plane translates to the XYZ plane. But what happens to a polar coordinate system? The polar coordinate system basically just gains another axis of Z, exactly like the Cartesian coordinate system, except we keep the XY plane in polar coordinates defined by r theta. So how does that look? X, Y, and Z. And our point here, if we have some point like here, this point is defined by P, X, Y, Z from the Cartesian coordinate system. But now in the cylindrical coordinate system, it would be defined as P, R, theta, Z. And R theta defines its polar coordinates here. So if we take it down here, this over here would be our R value, and this over here would be our theta value, while this stays as Z. That's the cylindrical coordinate system. Now, for some simple conversions between the Cartesian coordinate system and the cylindrical coordinate system, because you will have to translate between the two while you're solving some problems. So, conversions. The conversions between cylindrical and rectangular coordinate system, rectangular being the Cartesian coordinate system, we have x equals r cosine theta, remember, from polar coordinates in Calc 3. Y equals r sine theta. Z stays the same throughout these, so don't worry about converting Z because it's constant. Some more things to consider: r squared equals x squared plus y squared. Tangent theta equals y over x. And yep, these are pretty much all the conversions that you'll really need, like the base conversions. Now, to help you visualize more of the cylindrical coordinate system, I'll show you some examples of some of our values being constant and what kind of shapes they would make. So, let's draw our axes. If we have a constant r value, where r equals c, some c being some constant, then our shape here would basically have every point on this graph would have radius r from the origin. But we have to remember that that doesn't mean that you can have some point here with radius r. Instead, you have a point here on the xy axis with radius r. And then we can have this make a circle on the xy plane because radius. And then if we bring it up 1z, we have another circle of radius r with a different z value. So eventually this forms a cylinder, an infinitely long cylinder of radius r. Now, what if we had some constant theta value? Recall, theta is the angle from the x-axis. So, if we have some constant theta value, or theta equals c, this would be theta equals c with some plane here, some plane that's of angle theta from the x-axis. So if we have the x-axis here, our plane could be here with some angle, and it would be infinitely long. Now, what if we had some constant z value? If we have some constant z value where z equals c, then we can draw a plane here that's parallel to the xy but perpendicular to the z-axis at some constant value of z equals c, and it is infinitely long. That's it for conversions and examples. Now, let's learn how to integrate on the cylindrical coordinate system. But first, let me give you some basic shapes to remember so that you don't get confused when you're drawing it to help you integrate. So some basic shapes to remember. I'll give you the rectangular coordinates too. So a circular cone, x plus y squared equals c squared. And this is just r equals c. Because this is r squared equals c squared, take the square root, so that's how you derive that. Sorry, this should be a cylinder. This is a circular cone. C squared equals c squared, x plus y squared. This is z equals cr. And a couple more to keep in mind. Sphere. And one more, a paraboloid. Now, actually, the good part, integration. So let's integrate on the cylindrical coordinate system. So, Fubini's theorem, these together, Fubini's theorem for cylindrical coordinate system with a rectangular box B on the cylindrical coordinate system. So not a general region, this is just a cylindrical, or this is just a rectangular box. So where B is subject to these constraints. Oops. So then we can say that g of x, y, z, what it used to be on the Cartesian coordinate system, is now converted to g r cosine theta, r sine theta, and z. So these are just our conversions from before, and z stays the same. And we can set this to just a function of r, theta, and z, because we've converted everything to r, theta, and z. Now, what does this mean for our Cartesian coordinate system triple integral? What does it become? This is what it becomes. So start with our original. Then becomes these, the bounds for z, bounds for theta, and finally our bounds for r. And remember to have the correct ordering for your integration constants, because you don't want to mix up your integration. Now that you've seen this, you're probably thinking, okay, how does it look? So let me draw something to help you visualize what's actually happening. So at some, if we have, this is the shadow. This is the shadow of the box onto the plane. This here, this angle, assuming that's straight, this angle here would be our lower bound of alpha. This one is our upper bound of beta, and the box that's actually up here, the box that's up here with some height, let's give it some depth, would be at some maximum height of D and some minimum height of C. And the minimum radius here would be R, minimum radius here would be A, maximum radius here would be B, and those are bounds for our R. And here, when we integrate it, we basically cut it up into very, 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 very small regions of volume, where each of these boxes, if we just take a box, can be defined as B, I, J, K, which is defined by Ri minus 1, Ri, theta, J minus 1, theta J, and Zk minus 1, and Zk, where our box, of course, is in coordinate system would actually be Rijk, theta ijk, and Zijk. Now, what about something that's not really good looking like that? What if it's a general region that we just need to integrate over, and it's not this nice box that's looking good? Instead, we can have some of our constraints be functions instead of constants. So that brings Fubini's theorem for general regions over a cylindrical coordinate system. So for some region that we need to integrate over E, projection All of this is in three-dimensional space, of course, where D is the projection of E onto the two-dimensional axis, the r theta plane in this case. So we have this, the original integral r dr d theta dz. As you remember that dA is r dr d theta. Now we're just adding a dz to make it a volume and not just an area. Take the double integral over the projection of the single integral of the upper bound of the box, which is defined by a function, and the lower function of the box, and of our OG function dz, then integrate with dA. Remember, dA is r dr d theta. Don't forget that. Don't forget the r. A lot of people forget the r. And make sure that your integrating constants are good with your order of integration here. And we can generalize this even more. We can generalize this even more. We can take this off and have this be theta equals b, theta equals alpha, r equals g1 theta, a function of theta. So on the r theta plane, you can make r a function of theta and have it as your bounds here. Yes, you can have multiple functions like this. You just have to make sure that you're integrating the right way to eliminate all the functions. So always have a constant there. And g2 theta up there, r equals g2 theta. And this is pretty much how you do it over a general region. And that wraps up cylindrical coordinates. Now, a little more abstract, let's move on to spherical coordinate system. This one's a little harder, I feel, because there's two angles to worry about and not just one. So what is the spherical coordinate system? So let me draw it out. It's a little harder to draw too. X, Z, and Y, of course. Now, if you have some point out here, some point out there, remember it used to be defined as P, X, Y, Z, but now we're going to be fancy and transfer it to spherical coordinates and have P, rho, theta, phi. So what is even happening here? What do those even mean? So of course we know X, Y, Z. Now if we want to define these, we can say that this here, the distance from the origin, which is located at 0, 0, 0, to our point rho, theta, phi, this length is equal to rho. So kind of like polar coordinates, but it's up. It's the actual magnitude of distance of the point, not just the projection onto the xy. So a little different. And this angle here from the positive z to our point up here too, this angle is phi, this angle is also phi. Now let's drop it down to the xy, and now we have this. This angle right here is our theta, and this length, if you remember from cylindrical coordinate system, is actually still r. And of course, this length still stays z. When you're finding your bounds for phi and theta, I highly recommend to draw it out and use two-dimensional coordinate systems to help you find that out. Now for some simple shapes. At some constant rho value, we have, that basically means that our distance on every point of our set is exactly some distance away from the origin in three-dimensional space. Very important, three-dimensional space and not two-dimensional space. Remember, from two-dimensional space, if it's the same distance away, it would make a circle. But three-dimensional space, we would basically have a sphere around it. This is a sphere around the origin of all radius rho. Now, if we have a constant theta value looks pretty much the exact same as cylindrical coordinate system. We just have a sheet, an infinitely long sheet that is of some angle theta. It's an angle theta away from the x. Now, this one, a little harder to think about. What about phi? We just did theta and rho. What about phi? If phi is a constant, then that basically means from the positive z-axis, it is the same angle phi away at every single point of the set. So, first, let's start with just one. One right there. And this obviously goes on forever and ever because our only constraint is phi. Now, let's draw another one here. This is also angle phi away, right there. That's also angle phi. Now, you may be thinking, what about here and here and here and here and here, out of the page and into the page as well? And you'd be correct, because it basically maps a upside down circular cone, which every single outward ray has an angle of phi away from the positive z-axis. And yes, that does mean that the maximum phi angle you can get without going over the negative z is just pi. Now for some conversions. Let's start with spherical to rectangular, which is the Cartesian coordinate plane. And then we'll get to cylindrical and spherical, because that is also very important to know. So let's start with this. X equals these are how you get from rectangular to spherical. Now let's do spherical to rectangular. Or no, sorry, other way around. This is how you go to rectangular from spherical. Now let's figure out rectangular to spherical. This is how you go from spherical to rectangular. Now let's work on rectangular to spherical. Oh my god. this is tangent arc cosine of z square root x squared plus y squared plus z squared. This is very important to know. Now, what about spherical to cylindrical? Spherical to cylindrical. Let's start with spherical to cylindrical, and then we'll move to cylindrical to spherical. Theta remains the same, of course, because theta stays the same because both of them use the xy plane as the polar axis. This is cylindrical to spherical now. And theta equals same, just put it down there. This phi becomes arc cosine of z square root r squared z squared. This is also really important to know. I suggest if you can't have a cheat sheet during your exam, memorize these formulas because you do not want to be deriving them in the middle of the test. It's just a waste of time. That wraps up conversions. Now let's integrate. So, our goat, Fubini, also has a general region formula coming down, but let's start with the overall, let's start with the simple bounded spherical box to start with. So for some box, let's define by this. Then we have our formula to be b g rho theta phi dv becomes make sure that you get your integration in the right order so that you don't mess up at the end. And our dv becomes rho squared sine phi d rho d theta and of course d phi. Couldn't fit it in, but know that d phi is there. This is also very important. You should have this either memorized or on your equation sheet, or cheat sheet, I guess. Now for Fubini's theorem for general regions. Both of these go together. Fubini's theorem in spherical coordinates for a general region is formally this. I'll write out the expanded version to show you the full picture of what's happening. So theta equals beta, of course, alpha. Now you can also have rho as a function of theta. If you have that, then you can put it here. Now phi's and phi will have a function defined with rho and theta. Then you can put it here too. Equals phi, of course. Then our trusty dv here, that's kind of long. Integrate in the correct order because you don't want to mess up on the exam. D theta. This is the expanded version for a general region of on spherical coordinates. This is Fubini's theorem. Of course, for a region that's defined on the spherical coordinate system, E, that has shadow rho theta onto the rho theta plane. D is the shadow, and D has constraints of rho, and it also has constraints of theta. This is how you do it in three-dimensional space. And that pretty much wraps up the video. Thank you for listening. I'll see you in the next video about Jacobians.